In the previous lectures, we have seen the calculation of carrier concentration and Fermi level in case of intrinsic semiconductors. Now, the same problem we will discuss in case of extrinsic or impurity semiconductor. Okay? It means you have discussed the calculation of carrier concentration Fermi level in pure semiconductor. Now, the same problem we will see in case of impure semiconductor, or you can say N-type semiconductor and P-type semiconductor. Okay. As you know that the donor or acceptor levels are present in case of extrinsic semiconductor depending on the type of impurity present in them. You know, in case of N-type semiconductor, the impurity atoms are pentavalent and they are also called donor atoms because they donate the electron to the conduction band. And so those impurity atoms are found in an energy level which is called donor energy level. On the other hand, you know, in case of P-type semiconductor, the impurity atoms or the doped atoms are trivalent and they accept electron, and so they are called acceptors. And those impurity atoms are found in an energy level which is called acceptor energy level. Okay. Actually, the concentration of donors or acceptors in a semiconductor affects the Fermi level and the carrier concentration of the semiconductor. Okay. So, to find the carrier concentration Fermi level, we will see the problem separately for N-type semiconductor and P-type semiconductor. Actually, in this lecture, we are going to see the calculation of carrier concentration Fermi level for N-type semiconductor. Okay? And I have shown here in this figure the energy level diagram, or you can say the band diagram for an N-type semiconductor. Okay? And you know, at 0 Kelvin temperature, that is at absolute zero, all the donors are in unionized state. You can see this is the valence band and the energy corresponding to the uppermost edge of the valence band. I have assumed EV, and this is your conduction band, and the conduction band and valence band, you know, is separated by an energy gap which is called forbidden energy gap or band gap, and we denote it by Eg. Okay. And the bottom edge of this conduction band is at energy level Ec. Okay. And I have considered here this an energy level which is called intrinsic energy level. This is intrinsic level. It means this is the Fermi level at 0 Kelvin temperature for the pure semiconductor. Okay. And this Ed, you can see, this level is called actually the donor level. And the donor impurity atoms are present in this energy level. Okay. And by this small spheres, I have shown some of the donor atoms present in this donor level. And you know, if temperature is equal to 0 Kelvin, okay, actually in that condition, the fifth electron of the donor atoms are not detached from the parent atom. Okay, and so they are unionized. Okay, they are not in ionized state. In other words, you can say that all the donor levels are occupied with electrons at 0 Kelvin temperature. Okay. But as the temperature increases slightly, some of the donor atoms get ionized and contribute electrons to the conduction band. For example, if you consider that this atom now becomes ionized, So from this electron will move to this conduction band. Okay, and we also considered that this atom also get ionized. Then electron will move to the conduction band from this atom. Okay, so with rise in temperature, some of the donor atoms will get ionized. Okay, and the energy needed, the minimum energy needed for this ionization will be equal to what? This will be equal to EC minus ET, minus ET. So at least when due to this thermal agitation, this much energy, EC minus ED energy, will be gained by the atom in donor level, then the electron will move from this donor level to the conduction band. Okay, and so due to this, no hole is created because this is extra electron. Okay, and so there is no hole in valence band due to this transition of electron from the donor level to the conduction band. Okay, and this energy delta E, which is equal to EC minus ED, this is the minimum energy required for it, and so this is actually called ionization energy for the donor atoms or donor level. Okay, and actually, when temperature is raised, then some of the valence covalent bonds in this valence band are also broken and electron will get freed, and so some of the electron from this valence band will also move to this conduction band. Okay, so this is the electron which actually comes to the conduction band after jumping from valence band. But this transition of electron from valence band to conduction band leaves behind it a hole in the valence band. This is the hole. This circle which is I am showing here, this is a hole. So you can say that if again one electron is moved from this place in valence band to the conduction band, then again a hole will be created, which I am showing here by this small circle. Okay, so there are two means of electron going to this conduction band. First of all, the electrons from the donor level move to the conduction band, and this is actually the fifth electron of the donor atom, that is extra electron, and so due to this the donor atoms get ionized, they get positively charged. Okay, but no hole is created. Okay, but the electrons from the valence band also move to the conduction band, and due to this transition of electron, holes are left into the valence band. Okay, so you can see that the number of electrons in conduction band will be much more greater than the number of holes in the conduction band, because due to a small rise in temperature, the probability of breaking of covalent bond in valence band is very little, but this extra fifth electron easily moved to the conduction band. Okay, so in this condition you can say that the number of electron is much more than the number of holes in the valence band, and that's why we can say that since the number of holes produced in this process is however very small and number of electron is very large, so you can say that the Fermi level must lie somewhere near the middle of the donor level and the bottom of the conduction level. So you can see I have shown this is the Fermi level, and due to the larger number of electron in conduction band with respect to the number of holes in valence band, we can say that this Fermi level must lie between the bottommost edge of the conduction band and the donor level. Okay, so EF has been shown between EC and ED. Okay, I think you have understand what I am telling to you. Okay, actually we will determine the equilibrium carrier concentration at a particular temperature T, and for this calculation let us consider that this Nd is the number of donor atoms per unit volume in the donor level, or you can say that this is the concentration of donor atoms, okay, unionized atoms. Number of atoms per unit volume means concentration. And ED, we have assumed that this is energy of donor level, as you can see in this energy level diagram. Okay. So, as we have assumed that the Fermi level EF lies more than few kT below the conduction band, the electron concentration in conduction band can be given by the same result which we have learnt in case of calculation of carrier concentration in intrinsic semiconductor. Okay, here you can say that the most probably the electron moving from the donor level and from this valence band will be just at the edge of the conduction band. Okay, so the concentration of electron in conduction band is given just by the formula which we have learnt earlier in case of intrinsic semiconductor, and you can remember that result, that N is given as Nc times exponential raised to the power minus Ec minus Ef over Kt. Okay, you know this Nc, which is actually called the this is actually the specific number density of conduction electron, and this is given as 2 times of 2 pi me star kt over h square whole to the power 3 by 2. You can remember it. This result we have already discussed in our previous lecture in very detail. Okay. So in this way, with the help of our knowledge of intrinsic semiconductor, I have written here this concentration of electron in conduction band on the basis of the idea which we have learned in case of intrinsic semiconductor. Okay. Now, now you can see, we consider that this Nd plus, this is the concentration of ionized donor atoms. What is this? As you know, when temperature is slightly raised from 0 Kelvin temperature, then some of the donor atoms get ionized. Their fifth electron move to the conduction band, and after losing the extra fifth electron, the atoms get positive charge and becomes positively charged ions. So as I have shown, this atom has been ionized, this atom has been ionized, but all of the atoms do not ionize. So Nd plus and Nd will be different, and Nd plus represent the number of ionized donor atoms in unit volume. So you call it concentration of ionized donors. Okay, but if Nd plus is the number of ionized atoms in donor level, then due to this ionization process, same number of electrons have been jumped to the conduction band. You can see, as in this figure, I have shown that there are 2 atoms ionized in this figure. Okay, and due to this, 2 electrons move to the this conduction band. So the number of ionized atoms in donor level and number of electrons in conduction band due to this will be same. Okay, so this is also equal to, this Nd plus is also equal to number of electrons moving from donor level to conduction band. Okay, I think you have got it. Okay, now we consider P equal to concentration of holes in valence band. But you know, the number of holes present in valence band and the number of electrons jumped from valence band to the conduction band is same. So this concentration of holes is also equal to number of electrons jumping from valence band to conduction band due to the thermal agitation. So you can see, if this is your conduction band, this gains energy from two sources. One from this donor level, okay, this is your donor level, and from here this gains energy, this gains electron, and on the other hand it also gains electron from the valence band, okay. So this is from valence band. So the total number of electrons in conduction band will be equal to what? That will be simply the sum of the concentration of ionized donor atoms, Nd plus, in the donor level, and the concentration of thermally generated holes in the valence band. Okay. So when you will add both of these, you will get the total number or the total concentration of electron in the conduction band. So N can be given as Nd plus P. Okay. I think you have clearly got it. Okay. But in N-type semiconductor, most of the electrons in conduction band are from the donor atoms. Only few valence electrons, or you can say only few covalent bonds in valence band are broken, and so the number of electrons from valence band to conduction band, reaching to conduction band, is very few. On the other hand, a large number of electrons move from the donor level to the conduction band. So you can say that actually in actual practice this Nd plus is much greater than P. Okay, Nd plus is much greater than P. And if Nd plus is much greater than P, you can neglect this P in this equation too, and so neglecting this P in comparison to Nd plus, we can say that this N is almost equal to Nd plus. So almost the concentration of electron in conduction band is equal to the concentration of ionized donor atoms, almost equal to. Okay. But you know from law of mass action that if a sufficient number of donors are present to produce electron in the conduction band, the concentration of thermally generated holes gets suppressed as a consequence of the law of mass action. Okay, because we know that in accordance with law of mass action, N times P is equal to Ni square. You can remember, you have already studied this. Here Ni is called intrinsic concentration. Okay, but we have seen that this N is almost equal to Nd plus. So we can write Nd plus times P equal to Ni square, and therefore P is equal to Ni square over Nd plus. Okay, P equal to this much. Okay. Now, now we will actually find the concentration of ionized donors. How we can find the concentration of ionized donors? You can see the ionized donors are present in the energy level having energy Et. Okay, its energy is Et, and total number of donor atoms is Nd, and among those Nd plus has been ionized, and we have to find the concentration of this Nd plus. So this can be found by the occupation probability. You know from Fermi-Dirac distribution function, f of E represents the probability of a particle finding in energy state E. Okay, finding in energy state E, and so if this ND atoms, we have to find the probability that ND atoms will be in energy level ED. That probability will be denoted by the symbol F of ED. Okay, but among these, some of have been ionized. So the probability of ionized atoms present in this donor level, that will be equal to 1 minus F of ED. 1 minus F of, because total probability will be 1, and so the probability of finding the ionized donor atoms in this donor level will be 1 minus F of ED. And when this probability will be multiplied by the total number of donor atoms, then you will get the concentration of the ionized donor atoms. Okay, so you can see I have written here that the concentration of ionized donors is given by Nd plus equal to Nd times this probability, 1 minus F of Ed. Okay, but what will be F of Ed? You know F of Ed in accordance with Fermi-Dirac distribution function. Instead of E here there is Ed, so you can write that this will be Nd times 1 minus 1 over 1 plus exponential raised to the power Ed minus Ef over Kt. At the place of E there is Ed here. Okay. Now taking LCM and simplifying it, you can see this is equal to Nd times E raised to the power Ed minus Ef over Kt over 1 plus exponential raised to the power Ed minus Ef over Kt. But as you know that here in denominator we can neglect this exponential factor in comparison to 1. It means the exponent term can be neglected in the denominator because the energy, Fermi energy EF lies more than a few kT, you can say, above the donor level ED. And so actually this exponential factor E raised to the power Ed minus Ef over Kt is much smaller than 1. And so we can neglect this exponential term in comparison to 1. And therefore, you can say that this Nd plus, which is actually the concentration of donor ions, that is given as Nd times simply E raised to the power Ed minus Ef over Kt. So in this way we have calculated the concentration of ionized donor atoms in donor level. But you can see this Nd plus in accordance with equation 3 is simply equal to N. So you can say, see, I have defined already the value of N here, okay, and Nd plus has been defined in this equation 5. So now let us substitute the value of N from equation 1 and the value of Nd plus from equation 5 in this equation 3, where we have written N is equal to Nd plus. So equating these two, you can see this is the value of N defined in equation 1. This is Nc times e to the power minus Ec minus Ef over Kt. And Nd plus, this is this much. This is Nd times e to the power minus Ef minus Ed divided by Kt. Here I have taken this minus as a common factor, so Ed minus Ef has been now written EF minus ED. Okay. Now actually simplifying this result, we can obtain the value of EF, that is the Fermi level or Fermi energy. And for this, let us take the natural log of both sides of this equation. So after taking the natural log, you can see of this equation, what will be your result? This will be natural log of Nc minus Ec minus Ef over Kt, because this is e to the power this much, and when you will take a natural log, this will be simply equal to Ec minus Ef over Kt. And in RHS, there will be log Nd minus this much. Okay. So this is log Nd minus Ef minus Ed over Kt. Okay. Now let us bring this last term in RHS in LHS, and this will now become plus. So this is Ef minus Ed over Kt and minus Ec minus Ef over Kt, and that will be equal to ln Nd minus ln Nc. Okay. Now you can see this will be Ef minus Ed minus Ec plus Ef over Kt, and this is log Nd over Nc, because log A minus log B, you know, this is log A by B. And this Ef and Ef will be added, so this is 2Ef minus Ed plus Ec, and equal to Kt times log Nd over Nc. Okay. So 2Ef will be equal to Ed plus Ec, bring this term in RHS, and plus Kt times natural log of Nd over Nc. So Ef is given as Ed plus Ec divided by 2 plus Kt over 2 times ln Nd over Nc. Okay. So this is the expression for the Fermi energy or Fermi level, and you can see this Fermi level depends to some extent on temperature T. Okay. And also on the value of Ed, Ec, Nd, Nc. Okay. These are the different factors. Now after getting this result for Fermi energy for N-type semiconductor, now we will discuss this result. What are the important facts that can be seen from this result? Now we are going to see it. So what are the important points? Actually, when you talk about this result A1, we have considered the temperature of the specimen equal to T, which is neither very large nor very small. It means all these calculations have been carried considering that the temperature is neither very large nor very small. It means you are talking about the moderate temperature. So actually this expression which we have obtained for the Fermi level or Fermi energy is valid only at moderate temperature. Why we are saying that it is valid only for at moderate temperature? You can see. In fact, by mistake, one can say that if T is equal to 0 Kelvin, T equal to 0 Kelvin, then what will be EF? Without thinking seriously, one can say that since T is 0, so this second term will vanish and EF will be equal to ED plus EC divided by 2. It means wrongly a person say in this condition that this Fermi level lies just between the bottom of the conduction band and the donor level. But this is a completely wrong interpretation, completely incorrect. When T is equal to 0 Kelvin, actually EF is not equal to ED plus EC. Why we are saying like this? Because you can see in this second term only T is present here not. but Nc is also present. And you know, in the expression of Nc, there is T actually, and you have to take that T also 0. And when you will done like that, the result will be something different. Let us see. I have written here that Nc is equal to this much. You know it. You have studied this thing several times. Okay. So from this result you can see that this Nc is proportional to T to the power 3 by 2. Okay. So when actually we will put the value of Nc, here there will be T to the power 3 by 2. And if you will take here T equal to 0, okay, then there will be log infinity, which is undefined. So you can't say that at 0 Kelvin temperature, EF is simply equal to this much and this second term vanishes. You can't say. Okay. So if anybody don't think seriously, not to think about this Nc or temperature dependence of Nc, then such a person wrongly says that at 0 Kelvin temperature EF is equal to Ed plus Ec over 2. But that is wrong. Okay. So you can say that at 0 Kelvin temperature, actually this equation is not valid. This equation does not hold because it gives an undefined condition, unphysical condition at 0 Kelvin temperature. Because I have told you earlier that this result has been obtained considering a moderate temperature. So if you are particularly talking about 0 Kelvin temperature, then this result will be not valid. Okay. So I have told you earlier that equation A1 is valid only at moderate temperature. Okay. Not at 0 Kelvin, and now we will see it is also not valid when T is infinite, and that is temperature is very large. Even then this result will be not valid. Let us check it. If you consider that T is tending towards infinity, it means you are talking about a very high temperature. Actually, when there will be a very high temperature, you know, a large number of covalent bonds will be broken and a large number of electrons will move from the valence band to the conduction band. In that condition, there will be a large number of holes P in the valence band. And so the condition which we have assumed here, that this Nd plus is much greater than P, this condition will be not valid when temperature is very large. Actually, in that condition it is possible that this P will become very large to the value of Nd plus. It is possible. So our assumption under which we have obtained this result will be not valid, and so this result will be not valid. Okay. So I have written here, you can see that when temperature is very high, Nd plus is not much greater than P. And when Nd plus is not much greater than P, you can't write that N is equal to Nd plus. So in this condition, N is not equal to Nd plus. And if N is not equal to Nd plus, then this result will be not valid because this result has been obtained on this basis. So what you are seeing here, you can see when we assume temperature is 0 Kelvin, then this result does not hold. Okay. When you assume that temperature is very large, even then this result does not hold. So what actually what we can conclude actually? We can actually conclude that this result is valid when temperature is neither very small nor very large, but temperature is at its moderate value. Only then this EF in this manner can be defined. Okay. So I have written that actually the only valid information obtainable from this equation A1 is that the Fermi level lies somewhere near the middle of the donor level and the conduction band edge at moderate temperatures. Okay. In fact, in this condition, you can say that the conduction band. Okay. This is actually particularly true for those values of temperature and the value of donor concentration ND, for which the second term, second term in equation A1 on the right hand side is negligible in comparison to the first term. It means this result will be valid when ED plus EC over 2 is much greater than KT over 2 times log ND over NC. Okay. Actually, as the temperature will increase, you can see this second term will increase, and so the value of EF will increase. Actually, in this condition, on increasing the temperature, Fermi level moves downwards and crosses the donor level. Okay, crosses the, you can see this figure. As temperature is increased, this Fermi level will move downward. Okay, and this will cross this donor level, and finally this Fermi level get coincided with this intrinsic level. Now Fermi level will be at this value, which is actually equal to Eg divided by 2, where Eg is band gap, you can see. So on increasing temperature, the Fermi level moves downwards, it crosses through this donor level, and finally further increment of temperature moves this Fermi level from its present position to the intrinsic level, that is at the level which is at an energy EI equal to Eg over 2. Okay, or you can say that this Fermi level coincides with the intrinsic level EI. Okay. Although this is not apparent from this equation which I have derived for this Fermi level, but this is true. Okay. So actually, in such a case, you can see as the Fermi level moves to the position of intrinsic level, so this extrinsic semiconductor now behaves like an intrinsic semiconductor. So this is a very remarkable fact. A question may be asked you in any interview, that can an extrinsic semiconductor like N-type semiconductor behave like an intrinsic semiconductor? Answer is yes. It is possible that an extrinsic semiconductor may behave like an intrinsic semiconductor. And this is possible when the temperature of the semiconductor is raised in such a manner that the Fermi level of the N-type semiconductor will coincide to the intrinsic level of the semiconductor. In that very condition, actually the extrinsic semiconductor behaves like an intrinsic semiconductor. Okay. So these were the important facts which we can see from that expression for the Fermi level of an N-type semiconductor. Now we are going to see the second part of the problem, and this is actually the calculation of free electron concentration in conduction band. Okay. I have already defined this concentration in the beginning of my lecture. In this equation 1, you can see this is the concentration of electron in conduction band. Now, as you have obtained already the expression for EF, so when the value of EF which we have obtained just now will be substituted in this equation 1, we can get the concentration N of electron in this conduction band. Okay. So let us see. N is equal to Nc times exponential raised to the power minus Ec over kT minus Ef over kT. I have repeated the expression for N. Okay. Now, let us substitute the value of this EF which you have defined, which you have obtained in this equation A1. Okay, and simplify then. So let us put it. So this will be Nc times exponential raised to the power minus Ec over Kt minus. Now EF, value of EF is substituted here. This will be Ed plus Ec over 2Kt minus 1 over 2 log Nd over Nc. Okay. After substituting the value of EF, you will get this. Okay. Now, after simplifying these first two terms, you will get this is exponential raised to the power Ed minus Ec over 2Kt. Okay. And plus log Nd over Nc whole to the power half. Okay, this has been written by using the property of logarithm. Okay, this multiplication factor will be in at the place of power. Okay. Now this will be Nc and e to the power this much into e to the power this much. Okay. So this can be written as e raised to the power log Nd over Nc whole to the power half times e to the power Ed minus Ec over Kt. But you know that e to the power log x, this is simply equal to x. Okay. So here this will be simply equal to Nc into Nd over Nc to the power half. Okay. And times exponential raised to the power Ed minus Ec over 2Kt. Okay. Now this Nc to the power half in denominator will cancel out and your result will be Nd times Nc whole to the power half times exponential minus delta E by 2Kt. Here delta E has been written for Ec minus Ed. Actually this is the energy of bottommost level of conduction band and this is the energy of donor level. And you know the energy needed for an electron from moving from donor level to conduction band, the minimum energy needed is Ec minus Ed. I have told you it earlier. And this is denoted by the symbol delta E. And this is called ionization energy for the donor. Okay. So Ed minus Ec, this will be minus delta E. So N is equal to a square root of Nd times Nc times exponential to the power minus delta E over Kt. Actually the page has been turned, but this will be okay, and let us see. Okay. And let us see. Now we will substitute the value of Nc. You have already known that Nc is equal to what? 2 times of 2 pi me star over Kt whole to the power over h square whole to the power 3 by 2. So after substituting the value of Nc, your result will be n equal to 2 Nd to the power half times 2 pi me star Kt over h square whole to the power 3 by 2 times e to the power minus delta E over 2Kt. Okay. So this is the expression for the concentration of free electron in conduction band in n-type semiconductor. And you can see that this concentration is directly proportional to the square root of the concentration of donor impurity. Okay. It means n is proportional to a square root of Nd. And you can also see that this n increases exponentially with increase in temperature T. As the temperature is increased, the concentration of electron in conduction band in n-type semiconductor will increase. And you have just learned that at very high temperature, this N-type semiconductor behaves as an intrinsic semiconductor because the Fermi level actually gets coincided with the intrinsic level of the semiconductor. Okay, so in this way we have calculated the value of Fermi energy EF and the concentration of free electron in the conduction band in case of N-type semiconductor. And I think you have clearly understand the calculations, and now in our forthcoming lecture we will see the same problem for the P-type semiconductor. Okay, thank you very much.